All right, 2.5, exponential function, context, and data modeling. And Rachel's going to be our first reader. Here we go.
Sometimes data from an exponential function does not display a proportional growth pattern. This is due to a vertical translation of the function. However, we can add or subtract a constant from the output values y to reveal a proportional growth pattern, then the initial function was also exponential.
All right, so again, sometimes our changes are proportional, and then we know it's exponential. All right, so let's go to example 1. Here we go.
Selected values from several exponential functions are given in the tables below. For each, find the constant value that can be added or subtracted to the output values to reveal a proportional growth pattern. Then write an equation to know the function.
All right, so let's write our equation of our function. So how do I go from 7 to 13? 6. Then what? 12. Then what? 24. And then 48. So what's happening to our changes? They're being multiplied by 2. And so when we have these multiplying by 2, it's growing at a proportional rate. So it's a what kind of function? An exponential function. However, what we don't know, so our function right now is a times 2. Our b is 2 because that's what it's growing at a rate of, to the power of x plus whatever constant. I don't know what I'm moving up and down. And so we need to actually solve for this a and c. And so what we're going to do is we're actually going to substitute in these ordered pairs. We're going to substitute in these ordered pairs, and we can actually find our a and c. So we're basically making a system of equations. Now, you can actually pick any two. I'm going to pick the ones with smaller numbers. Everybody follow me? So I'm going to pick the x's 0 and 1 whenever I can, so it deals with smaller numbers. So if I substitute in 7, that would be my f of x. So I'd have 7 is equal to, when I substitute in 0, 2 to the power of 0 is how much? 1. And so now I have a times 1, which is a, and then plus c. So my first equation is 7 is equal to a plus c. Now I'm going to substitute in my next ordered pair. So now I would end up having 13 is equal to, now when I substitute in 1, I'd have what? 2 to the power of 1, which is what? 2. So now I have 2 times a, which is 2a, and then I still have plus c. So now I have a system of equations, and now I need to solve them. And so what I personally would do is I would distribute a negative throughout this one. And so now I have a negative 7 is equal to a negative a minus c. And so when we add straight down, what happens to my c's? They cancel. And so now I'm left with 6 is equal to a. Everybody see how we got the a? And so what I'm going to do now is I'm going to substitute this 6 back in here. So now I'd have 7 is equal to 6 plus c. So what does c equal? 1. And so now I would have my function, f of x, is equal to 6 times 2 to the power of x, and then plus 1. All right, so how do I go from 2 to 10? 8. And then? 24. And then? 72, and then 216. Very good. All right. And so our rates of changes are not necessarily proportional. However, what is the changes doing? They're being multiplied by how much? 3. And so that's what makes it an exponential growth. Those changes are proportional. And so now I would end up having g of x is equal to a times what would my b be? It'd be 3 to the power of x and then plus c. And so what we need to do is solve for a and solve for c. And again, it can be any two. However, I'm going to use these first two ordered pairs. All right. And so now when I'd substitute in 0 and 2, I'd now have 2 is equal to, when I substitute in 0 here, I'd have 3 to the power of 0, which is 1. And so now I'd have what? A plus c. And now I'm going to substitute in my next ordered pair. Again, it can be any of them, but I'm going to choose this one. And so now I would have 10 is equal to, how many a's now? 3. I'd have 3 a's, and then plus c. All right. And so now I have a system of equations. I have two equations, 2 unknowns, and then we just solve. And so I personally am going to distribute a negative right here. And so what happens to my c's? They cancel out. So then what am I left with? 8 is equal to how many a's? 2 a's. And so what does a equal? 4. And so now that I have a equals 4, when I back substitute it, I'd back substitute it in this one personally, or it really doesn't matter. Let's do the top one. So 3 times 4 is what? 12. And then I subtract 12. So then C equals what? Negative 2. All right. And so now I have C equals negative 2. And so my function, my g of x, would equal 4 times 3 to the power of x, and then minus 2. All right, so on this one, how do I get from 63 to 31? Negative 32. Then what? Negative 16. And then? Negative 8. And then? Negative 4. And so those rates are not proportional. However, the rates of those are going to be. So what's happening from each one? They're multiplying by what? 1/2. I know we want to say divide by 2, but we want to be multiplying because I want that common ratio going on. And so I have 1/2 as my common ratio. And so now I have h of x, bless you, is equal to a times, what's my b? 1/2 to the power of x, and then plus c. And so now I need to solve for c and a. All right. And so now I'm going to use my first 2 ordered pairs. It doesn't really matter what you use, but I'm going to go there. All right. And so now let's substitute those in. So now I would end up with what? 63 is equal to what? A plus c. Now when I substitute in this 131, then I would have what? 31 is equal to what? 1/2 a, and then plus c. All right. And so there's my system of equations there. And so back in algebra, I personally don't want to deal with these fraction things. And so what could we do? We could multiply that one all by what? 2. We could all multiply that one by 2. However, I'm going to just multiply it by negative 2, and so I can cancel out my a's right away. All right, but you can multiply it by 2 and then go from there. But I'm just going to multiply everything by negative 2. All right, and so then I end up with what? Negative 62 is equal to negative a, and then minus, not c, but 2c. All right. And so then I have 63 equals a plus c still. And so then when I add straight down, what happens to my a's? They cancel out. And so now I'm left with 1 is equal to how many c's? Negative c. So what does c equal? Negative 1. And so from there, I can just take that and I can back substitute it in right here. And so what does a equal if c equals negative 1? 64. So a is equal to 64. And so now my h of x equals 64 times 1/2 to the power of x, and then minus 1.
An exponential model can be constructed if we are given either the common ratio and the initial value for 2 input-output pairs. We can find the initial value and the base common ratio with these 2 pairs. Example 2, for 0 is less than or equal to t, which is less than or equal to 30 minutes. The number of fans inside a large sports stadium can be modeled by the exponential function f of t equals a of b to the power of t, where f represents the number of fans inside the stadium t minutes after the doors open. There are 47 people in the stadium 2 minutes after the doors open, and there are 2,602 fans inside the stadium 20 minutes after the doors open. Use the given data to write 2 equations that can be used to find the values for constants a and b in the expression for f of t.
All right, fantastic. So f of t is this exponential function. And then they give me 2 items, basically. They give me 47 people in 2 minutes, and then they give me this 2602 in 20 minutes. All right, and so what's my input value? Is it minutes or people? Minutes are my input value. And what's my output value? My people. All right, and so all we're doing in this part 1 is literally just substituting in 2 for t and 47 for f of t. That's all we're doing. And so now we'd end up with what? A times b to the power of 2 is equal to 47. And then the other one would be what? A times b to the power of 20, which would equal 2602. All right, and that's going to be the exact type of problem in FRQ number 2, the first part. So on our calculator, let's go to stat, edit again, and put our input values of 247 and 20, and then 2602. Right, and so then it will say find A and B. And so how many are we going to round to when we find A and B? 4. And so A would equal this 30.0890, and B would equal this 1.2498, it looks like. All right.
Do I read the natural base?
No, we're on example 3.
Oh. Wait, okay. Selected values of the exponential function g are shown in the table above, where g of x equals a times b to the power of x. Use the given data to write two equations that can be used to find the values for constants a and b in the expression for g of x.
All right, so again, we're just going to substitute in. And so now we end up having what? 21.54 is equal to what? A times b to the power of 3. And then our other one is going to be what? 3.62 is equal to a times b to the power of 8. And literally, that's 1 point on the AP exam. So then how do we find the values of A and B? We're going to put that into our what? Our calculator, our stat edit. And then we're going to calculate that regression. All right. All right, so when we do our stat edit and then we calculate our regression using the exponential regression, we end up getting A is equal to this 62.8012, and our B, we have to round to 4 decimals, and so it's really 0.7000. However, I don't want to think that hard a lot of the times, and so a lot of the times I'll just be like 0.699991, and it's at least 4 decimals worth. All right, and so that's kind of how I kind of would do some of those. Oh, hold on, go ahead. All right, so the natural base E. I want to give a history lesson real quick. This is named after a dude. His name was Leonard Euler. All right, he is the sole responsibility for the natural base E. He's the one that discovered. It's an irrational number, kind of like pi. So everybody's customary with pi, 3.14159.265, so forth. But E is this 2.71828. 1/8, and then it doesn't have a repeating pattern after that. That's what makes it irrational. However, this is a natural base E. All right, keep going.
The natural number e is often used as the base in exponential functions that model contextual scenarios. Example 4, the number of bacteria b in a particular culture can be modeled by the exponential function b t equals 17e 0.31 t, where t is measured in hours. Let a t equals a times b t be an equivalent expression for b t. Find the value of b.
All right, fantastic. So right now, this is 17 times e to the 0.13 t. And then they just want it a times b to the power of t. Well, what is b then? B is the same thing as what? This e to the 0.31. All right, and so that's the answer. However, we're going to round to how many decimals? And so e to the 0.31 is 1.3634. All right, part B.
On the average rate of change of bt for the interval from t equals 1 to t equals 7.
All right, what is an average rate of change? Algebra slope. It's just algebra slope. And so what we want to do is find b of 7 minus what? B of 1 over 7 minus 1. All right. However, here's a quick way to do things. All right. What I want you to do is actually go into y equals, and I want you to put this function in as y equals that. And so now once we get that into y, our y equals, now we're going to go back into our main screen, and we're going to actually find the average rate of change using your alpha trace. All right, so then we use alpha trace to get to the y1 of 7 minus y1 of 1 over 7 minus 1, or 6, and then we press enter, And then we end up getting this 20.9521. Okay.
Find the number of bacteria be predicted by the model in 15 hours.
All right, so all we're going to do is find what? We're just going to substitute in 15. All we're doing is substituting in 15. All right, and so we can do this alpha trace y1 again of 15. All right, and so we ended up with 1,777.9448. All right, so one more example on these notes.
After 50 deer were introduced to a large wooded area, the population of deer in the wooded area can be modeled by the exponential function d of t equals a times b to the t, where t represents the number of years since deer were first introduced to the wooded area. The population of deer increases by 13% each year.
Keep going.
A. Find the values of A and B and use these values to write an expression for d of t.
All right, fantastic. So what is my A? It's my initial population of deer. So what's my A? 50. Because really, my ordered pair would be 0, 50. All right. Now my B is my growth rate, my ratio. And so it says the deer increase by 13% each year. And so what do I put that as? I put 1.13, exactly. So my B is actually 1.13. Where'd the 1 come from? Because that's already at 100%, exactly. So it's 13% more. Now, I want to go a little bit backwards on this. What if it was a decrease by 13% each year? Then it would be what? Point what? 87. How did we get 0.87? We subtracted it from what? The 100%, exactly. All right, and so this is an increase in my deer, and so my D of t would end up being 50, and then times 1.13 to the power of t. All right, part B.
According to the model found in part A, what is the population of deer in the large wooded area after 6 years?
All right, so all we're going to do is substitute in what? 6. So we're going to find D of t, we're going to find D of 6. Now, I'm personally going to put that in as y1, and so then I'm just going to find y1 of 6. All right, so we end up with 104.0976 deer after 6 years. All right, and so then let's talk about part C.
Find an equivalent expression for d of t, where t is measured in months instead of years.
All right, so this equation right here is in terms of years. Okay, now I want it in terms of months. Well, how many months are there in a year? 12. And so now my D of t would end up being this 50 times 1.13 to the power of what? Not 12t, but what? T over 12. Because now I'm inputting months in, but I want it to be equivalent to years. Now, what if it were in months first, and then I wanted it in years? Then it would be to the power of 12t, all right? But this way I'm going backwards, all right? Now we're going to find out the time in years it takes for the deer population to be 100, all right? So what are we trying to do here? We're trying to solve for what? T. We're solving for t. And so we're going to set this D of t equal to what? 100, all right? Now, we could use our algebra skills here. However, I'm going to do it graphically. So let's go back into y equals. So we graphed our original function and we graphed 100 and we solve for an intersection by using second calculate intersect, and then it will snap to where our time is equal to this 5.6714 years. All right, and so it happened at 1.56714 years in which that population was 100 deer. All right.